Yeah, excellent. Right, and you can hear me okay. Fantastic. Well, thank you very much for having me. This is a presentation to talk about the Great Western, what we call the fast charge battery train trial. A little bit about my own background. I'm a rolling stock engineer, so apologies for that. Of about 15 years in the rail industry, probably more now. Started off at Bombardier in Derby and ended up at a little company called GWR, which I'll talk a bit about in a minute, in 2018. GWR went bust in 2022, sadly, and then ended up at Great Western doing this project. So that's the potted history. The project itself is based on the West Ealing to Greenford line in West London. It's all about trialling a charging system for a battery train, because obviously if you've got a battery train, it's inherently range limited compared to a diesel train. You haven't got the overhead line or third rail to keep you going forever. So you need to find a way of charging it in a reasonable time frame. The charging system itself is located at West Ealing, the Bay Platform 5, and the line was chosen, of all the Thames Valley branch lines, this was chosen because it was double track, which means we could operate the battery train in trial mode, if you like, alongside the regular service train. So if anything goes wrong, it wouldn't scupper the service. And it's also nice and close to Reading Depot, where obviously a train is now based. The project started life as under Viva Rail as a supplier of the train and the fast charge system to Great Western as the customer. This is all sponsored by Department for Transport and Network Rail. But when Viva Rail went bust, Great Western purchased the assets and the intellectual property and took on 9 engineers, including myself, to keep it going, because such was the interest from the Department for Transport to see this thing happen. So it's been quite a roller coaster of a time. We started this really, we started in anger doing this project at the end of 2021, and it's now, middle of 2024. So you can see with the with Viva going bust and everything, it took a bit of time to get us back on our feet and remobilise. But here we are. Obviously, the project's got 3 main ingredients really. There's obviously the train and the charging system, but also the people. And I just wanted to emphasise that because really, without one of those 3 things, it probably wouldn't be happening. I always like to start my presentation with a little nod to Adrian Shooter here, who some of you might know. Was a big name in the rail industry. Started his career on the British Rail, worked his way up very quickly, and became the managing director of Chiltern Railways at privatisation, and did an awful lot to transform the Chiltern route from Marylebone up to Birmingham and all the rest of it. So if you haven't read these books already, I well recommend them. There's one about his life in engineering, and there's one specifically about the Chiltern Railways story, but it's fascinating stuff. I had the privilege to work for Adrian from 2018 to when he sadly passed away at the end of 2022 with motor neurone disease, but he was very much the driving force behind the project and the team. A little bit more about Adrian actually is Adrian wasn't just into railways, he was into, well, everything mechanical really, and he had amassed a collection of interesting vehicles, quite a few cars, but as you can see also a hybrid of the 2. He had a Ford Model T mounted on a 2-foot gauge chassis, which he ran around his garden railway in Oxfordshire. I met Adrian as a result of when I was at university, Imperial College Railway Society, and he became our president. And the students at Imperial College have this old car called, they call it Bow. It's a James and Brown model, which you won't have heard of because I think they stopped making cars before the First World War. But that car there, owned by the students, and I used to drive around central London, and I gave him a lift in it once, and he said, "Oh, I was so excited." He said, he used to say, "Dave nearly killed me in that car," because the brakes weren't very good. So that was when I first met Adrian, and then about 12 years later or 15 years later, I ended up working for him at Viva. And I just saw that advert there that James and Brown cars won't wear out, which was quite a sort of a statement to make. And Adrian often made statements like that, which you just think, as an engineer, why did you say that? But anyway, so that's a bit about Adrian. And then the team as it is today, as I say, there was 9 of us that came over to Great Western, but we've been very much brought into the Great Western family, supported by people in, program management, procurement, and all the rest of it. And somehow the team sort of inspired a sort of motivation around us. I mean, you can just see in the middle picture at the bottom, when the train first went to West Ealing back in February, it immediately got graffitied. and within a few hours, the entire team was out there cleaning the graffiti off. Such was their sort of interest and enthusiasm for this project. So it's really nice to see it's brought people along with it, and everyone sort of believes in what they're doing. So we'll start. That's the team, if you like. Now we'll talk a bit about the train. There's only one train. Well, there's other trains that are ready to be converted, but we've got one working train at the moment, a battery train, 3-car, multiple unit. It originates as an underground train, D78 underground train, which used to run on the district line in London. VivaRail developed this range of variants, if you like, of what became the Class 230, starting with a diesel-electric prototype. The big idea was to convert these D78 stock trains into diesel trains at first, to fill a gap in the market. So the first prototype was a diesel-electric multiple unit, and how that came about is a whole presentation in itself. That then evolved into a 2-car version. Then we created a battery prototype demonstrator. Then we merged the two into a diesel battery hybrid scenario, which is the ones that they're using in Wales now. We created a 3rd rail variant for the Isle of Wight. We exported 2 to America, and then finally we built or we converted the original prototype, the 23001, which is the electric prototype, into sort of a 2nd generation battery train with different type of batteries on it, and other changes. And then that's the train that we've ended up running the fast charge trial with. So you can see the sort of rapid evolution of the product, and that was one of the reasons I think why eventually VivaRail collapsed, is that we probably tried to do too much too soon. But as I say, there was a lot of work that went into, well, a lot of types of train that came out of 8 or 9 years of development, and it was a very interesting place to work, I could tell you that. This was the state of the train after it had done its stint as a diesel electric multiple unit. So it did some mainline running, sort of demonstration mode, carried some dignitaries, then had a nasty fire as a result of one of the diesel gen sets underneath. And after that, it stood in the field at Long Marston in Warwickshire, essentially moulding away. And then at the end of 2021, beginning of 2021, Adrian said, we're gonna take a train to COP26, which was the climate change conference, which took place in November 2021. So we said, we're going to convert this into a battery train, and we've only got 9 months to do it. So we took the train out of the field, gutted it again, and rebuilt it as a battery unit. But it wasn't just that. We had to not only put batteries on it, but we had to fit an extra battery. Now, the original battery train prototype, which is not that one, only had 2 large batteries fitted to the underframe, and Adrian wanted 3. So we contrived to fit 3 traction batteries. They're not small. Each one weighs 1.7 tons and is about the size of sort of 2/3 of this table, about 2 meters long by a meter wide by a meter deep. So to do that, we had to relocate other bits of underframe furniture, if you like, and find space for the various sort of supporting systems. So we did that by relocating main air reservoir, finding space for this 3rd battery, and each battery also needs a DC-DC converter, which is there to essentially supply the onboard thermal management system on the train. Because the batteries themselves are at 666 volts. I don't know who chose that as the number 666, but that's each the number of the beast. That's the voltage, the nominal voltage that each battery raft sits at. But they have this onboard cooling unit as well, which is at 96 volts. So these DC-DC converters have to take that voltage, step it down, which is not probably the best way of doing it, but that's what we had. The batteries themselves are from a company in Germany called Hoppecker, and I'll come on to that later as well. So lots of underframe rearranging to do. Not only that, but you've got to find space for the cables, because the cables are not insignificant as well. So we had to actually, in order to route the cables within gauge, we had to take up some of the floor and create this sort of hybrid floor where we hang the cables from underneath the floor. The floor is also a fire barrier, so it performs 3 functions: carrying the cables, providing the floor, and being a fire barrier. So there was a lot of engineering to do around that as well. And that's just a diagram to illustrate the start of that design process. This is and it ended up as being a heavy train. I mean, not unexpectedly, batteries are heavy. and it was the heaviest Class 230 that we ever built. 96 tons tear, as in no passengers. That's the total weight of the 3-car unit. Potentially up to 37 tons of passengers if you ever crush loaded it, giving 133 tons total crush loaded train. But in honesty, it will never get to that levels, but because the Greenford branch never sees that many people. But it does show, the challenge of fitting batteries to a train is not only space but mass as well. And of course, you've got to respect other things like the axle loading, the body shell, structural integrity, and all those challenges, and the gauge, because obviously you can't design stuff that sits outside a gauge. And we haven't got the luxury in this country of putting batteries on the roof like they do in Europe and other countries where you've got a more generous loading gauge. So quite often you'll see the Siemens battery train, and then Alstom, I think, have got one where the batteries and all the electrical stuff's on the roof because they can. So that doesn't help with the centre of gravity really. All the while we were doing the heavy duty engineering underneath, we were also changing the interior to make it look much more like a new train. We fitted a wide gangway at one end. These trains used to have just doors and no normal through route, but we fitted a walk-through gangway. New types of seats, new types of tables, draft screens. I mean, you go in it and you think that's a new train. That was one of the objectives really of the Class 230, was to make it look and feel like a new train. And we did make it to COP26. We demonstrated the train for 2 weeks, running in and out of Glasgow Central. We took it down to Barhead. We ran it over the Forth Bridge. So allegedly the first pure electric train to run over the Forth Bridge, and definitely the first underground train to run over the Forth Bridge. So that was very exciting. We were running in and out of Glasgow Central alongside the Porterbrook Hydroflex, which is a hydrogen train. Although they weren't actually running on hydrogen, they were running on the overhead line. They did tell anyone that though. Not that there's any competition, of course. So, onto the fast charge system. Well, I mentioned earlier that with a battery train, you've got limited range, really, and you can't really get away from that unless you carry on board range extenders like diesel engines. So you have to find a way of charging the train in a practical way. What isn't practical is having the driver having to get out and plug it in, or having to sit around for 3 or 4 hours at a terminal station, or even switching a battery raft, which has been suggested, because they're just so enormous, you just practically couldn't do it. So the way that we came up with at VREL was what's now sort of called the fast charge system. So what it consists of is, first of all, you need the kind of currents you're talking about to charge a train are pretty high, and you can't normally pull that sort of current out of the national grid. So you need some sort of energy buffer, and that's what the fast charge battery bank is. Now that's just a 20-foot container, shipping container with batteries and power electronics in it, and essentially that sort of trickle charges when there's no train around or overnight. And with that energy buffer, you've then got the power you need to charge the train in a short time scale. Then you need a connection between the trackside battery bank and the train, and that consists of charge rails, which are in the forefoot, and some shoe gear on the train that essentially deploys to connect with the charge rails, only when the train is stationary on top of the charge rails. And then when the train moves away again, after it's finished charging, the shoes retract and off it goes. There could have been several ways of doing that, the shoe gear. One would have been to put the shoe gear on the bogie, which is sort of traditional. We didn't want to do that, A, because the bogie is quite a high vibration environment and it would probably shake itself to pieces, or certainly lead to a design challenge. So we mounted it on the underframe, as in the same environment, vibration environment that the passengers are in, what they call the secondary sprung environment. And that's just to reduce the fatigue loads into the shoe gear. And it also means that you could take that shoe gear and apply it to another type of train. We've got to remember the Class 230 in use on this trial is only there sort of as an accident of history, really. But the idea is this system would be applicable to other types of trains as well, new or converted. And then I didn't mention it, but you've got the connection to the national grid as well, which is in theory a lower power and cheaper connection to procure, although it's taken us 2 years to get the DNO connection from Southern and Scottish Electricity, or SSE. So it still takes time to get the connection. So those are the main ingredients. Just to show you what it actually looks like, got a little. Oh, I didn't also mention the way in which the train communicates with the trackside equipment. That's through RFID tags, which are the normal RFID tags used for power changeover on the, for example, on the Class 800s running up and down here. When they go from diesel to overhead electric, they get the message comes through these RFID tags, which are attached to the sleepers, and the train itself carries a reader. And there's, in the case of our system, there's 3 of these RFID tags. The first one, there's a little graphic that should come up in a minute. The first one says train approaching, so we call that the sort of station confirmation tag. Then another one says lower the shoes when it gets a bit closer and it's below a certain speed. And then the final one is when the train is in the right place. And some other interlocks have happened as well. There's some actual hardwired proximity sensors as well to pick up the fact it's the right train in the right place. But the third one says, right, ready to initiate fast charge sequence now. And it's important to note that the rails you see there in the 4 foot, those are not live most of the time. When there's no train around, those are not live. They're earthed, they're perfectly safe. We treat them as they're live because that's just the right thing to do, but they're actually not live until the train is covering them. The shoes are on top of them. There's a little proving current that takes place before the full fast charge current happens, just to prove that you've got continuity and there's no earth leakage or anything like that. So there's all kinds of levels of interlocking and protection in the system to ensure it's safe. Because one of the battles was, when we wanted to do this originally, obviously those rails are seen like third rail, and there's a sort of assumption against third rail. I don't think there's anything to say you can't have third rail, but there's definitely assumption against it if you can avoid it. So we've always been keen to stress that it's not third rail. It just happens to look like it. Now you can just see there are three rails there. Go back a bit. There's one long one in the middle. That's the positive charge rail, and then there's 2 shorter ones either side of it. Those are the negative charge rails. The reason there's 3 is because the shoes on the train are the positive ones in the middle, on the centre line of the train, and the negative ones offset. There's only 2 shoes on the train, but 3 rails. That's so that if the train comes in the other way around, the positive shoe is always in the middle. So the negative shoe might go from left to right, but the positive ones are. So there's no clever switching involved for polarity. It's the positive rail is always in the middle. Although if you sit and work it out for a 3-car train, it makes no difference. It's only if you had like a single car train where it would make a difference. But anyway, the system is designed to be that way. This is a bit of a power flow diagram, if you like, indicating what happens at various stages. So the blue arrows are what happens with the power when the train is not around. You've got starting at the bottom, you've got the motors in the wheels, and you've got the traction control unit on the train. That's the brains of the outfit, really. And then the shoe gear and the traction batteries, if you like, connect to the traction control unit. And if the shoe gear is down, it's charging the batteries via the TCU, and if the shoe gear is up, then the traction battery is just providing power to the motors. It's as simple as that, really. Yeah, that's all. I mean, there's batteries in the fast charge battery bank as well, which are connected directly to the train when all the interlocks have been proven. But when the train's not around, those batteries are connected back to the grid. There is the potential in the future for the battery banks on the ground to feed back into the grid. Ours doesn't do that at the moment. That would be beneficial, if you like, for grid balancing, because that's becoming increasingly popular when there's a surplus of renewable energy, and the grid's looking for something to do with it rather than having to waste it. So there's a potential with the system to provide a benefit to the national grid as well. Back to the train. These are what the batteries look like. As I say, they're heavy, 1.7 tons, quite complicated. They are essentially lithium-ion batteries, although the chemistry is more complicated than that. It's a sort of hybrid chemistry between lithium iron phosphate and lithium titanate, and it depends whether you're talking about the anode or the cathode, and I won't go into that, but that's what they are basically. They are force cooled, so when you charge a battery, it creates a lot of heat, you need to get rid of the heat, especially if you're charging at high charge rates. And we are talking quite high charge rates of this, more than your average Tesla. And so you need to take the heat away. So they have active cooling inside them, which is to say that there's circulate air around the cells. The cells, if you like, are like an A4 book with air gaps between each one. And then, as I said before, there's a onboard HVAC unit which tries to maintain a steady temperature. So when it's charging or discharging, it's creating heat, and you want to keep that at a steady state. But also in really cold weather, you need to keep these batteries warm. Otherwise, the range drops off. And part of this trial is that we're going to try it through all seasons as well. Cold, hot, rain, sun, all the rest of it, to see what really happens. A lot is said about fire safety, obviously, with lithium-ion batteries or any battery. And unlike the average e-scooter, this has many, many layers of safety features, right through from the chemistry itself, which is one of the most stable chemistries that you can use for batteries, through to the way the thing is mechanically designed, short circuit protection. There's various fire barriers inside it, and if all of that fails to prevent thermal runaway, because thermal runaway is the thing you're trying to guard against, then there are downstream measures to actually mitigate the effects of that. For example, things to arrest the really nasty fumes that would emerge, and things to try and prevent explosions happening. So, as you can imagine, an awful lot of work's gone into the safety case for the batteries themselves. And this diagram is a nice diagram that we got off the Warwick Battery School, which we've all been on, which explains really all the various measures from things that might initiate thermal runaway right through to things that will arrest it. And it's that way of thinking that you have to get into, because there's no fire suppression system on this train. I mean, if you did get thermal runaway, there's nothing you can really do about it, other than dump the train in a massive tank of water, because what you're trying to do is cool it down. And you'll see now that fire brigades across the country are developing new ways of tackling EV fires, because whilst they're actually less likely to catch fire than the average internal combustion engine, when they do catch fire, obviously they're harder to put out. So a lot of work's gone into that. This is just a picture of the fast charge battery banks. As I say, it's a 20-foot container with an aircon unit on the side of it. Same principle applies as on the train. We're trying to keep the batteries inside in a stable environment. Half the container is devoted to the batteries in racks, and then the other half has got the switchgear in it. On the outside is an emergency stop button. Should you need to stop things in emergency, there's also an emergency stop button on the end of the platform at West Ealing, which is all designed to allow for anyone who might be around witnessing an incident can just hit that button and stop the charging process. Oh, I don't know. Oh, it's the same principle really for the battery rooms. So the shoe gear. This has been the bit where I've been most involved really. We developed the shoe gear. And there's no real precedent for this because, well, there is obviously the shoe gear on trains, but not using it for what we want to use it for. So we built a little test rig at Viva Rail's old premises in Southam in Warwickshire, and we, as you can see, it's quite a Heath Robinson contraption. It consists of two permanent way trolleys that we had. One is chained to the ground or chained to the end of the track. The other one translates, and it's propelled by an air cylinder, basically. So we set this up so that we could cycle the shoe gear backwards and forwards. You can do finite element analysis on the structural design of all this to a point, but it doesn't really, as there's no sort of load cases out there that there's no sort of proper service experience. We thought, well, we better test this in real life. So I say the front P-way trolley there would go backwards and forwards. Every time it comes forwards towards the rails, shoes would come down, the shoes would ride up the rails, stop, retract, and then the trolley would go back again, and it would just do that. And we think we did something like 20,000 cycles. And we also tested it in various weather conditions. We put leaves on the rail, we put ice on the rail. In fact, we contrived to make some sort of artificial ice, and then the next day it snowed. So that was nice. So we did that and recorded it, in great detail, the wear on the shoes, any sign of movement. This was all done without any current passing through the shoes, I should say. So what we also did was took the shoes to a test lab somewhere and did some high current testing. What we wanted to make sure, you have to ensure a certain contact pressure between the shoe, which is a carbon copper composite. You have to always maintain a certain pressure between the shoe and the rail in order to ensure good conductivity. Let me turn my phone off, sorry. What we did originally, we tested it on rough old third rails, cast or steel rails that were horrible, rusty, bent and twisted, and all the rest of it, just to see whether it could cope with that. And then we tested it on the rails we're actually using are aluminium with a stainless steel top on them. So they're very much better, now than the ones we tested them on, but we wanted to test it, in a worst case condition. And we also tested the shoe at different contact pressures. The shoes are propelled down with an air cylinder and they're also retracted with an air cylinder. So it's, the air pressure is quite critical to maintaining a good surface contact between the shoe and the rail. So we tried it at different pressures as well to see what difference it made to the heating of the interface. By and large, everything was fine. So, I mean, now we're into real life testing with the train on the track. We originally tested this system at Bletchley Depot near Milton Keynes with some short lengths of charge rail, which is what you see on the left picture, purely because the site we were testing it in was geometrically constrained. But the charge rails in real life are about 3 or 4 meters long. Here's a little video which should work of the test rig in action. So it goes along there, pushes all the snow out of the way, and this is the one where it was actually snowing, and then it retracts like that. And as you can see, it's quite effective at clearing the rails. And then this one is the system in action at Bletchley. You have to ignore the sort of sheet of plastic that was just there to protect the concrete, because the shoes actually drop slightly below the level of the rail in real life, but here there was a concrete apron. So we didn't want the concrete ripping the shoes. So you see it coming along, and in a minute you'll see the shoes drop down onto the plastic thing, slide along. That's where we'll get to, then up the rails, and then stops. So it's not very exciting, but it all happens automatically, and the driver has to do nothing at all. All the driver needs to do is stop the train in the right place. And the only indication the driver gets that anything is happening is a little light on the dashboard that says, I'm fast charging. So that's the interesting mechanical bit. Back to the paperwork, if you like, there was a lot of it. There were a lot of approval processes to merge together, as you might imagine. First of all, there was the sort of independent assessment of the train itself, for which we used an independent competent person. Then there was all the gauging and compatibility work to do, because obviously the train has got to be compatible with the infrastructure, not just at West Sealing, but everywhere it's going to run. So we had to go through all of that. Then there was the actual assessment of the system itself. So the fast charge system was deemed as a significant change under the common safety method regulations. Not the batteries itself, actually, just the system, because batteries had been done before, so that was already sort of in the bag. But the fast charge system was deemed as a significant change. So we had to go through the full ASBO process, as some of you might know about. So we appointed an ASBO, and then it has to also go through Network Rails process, which Peter very helped us with. And then after it's gone through all of that, we get what's called a declaration of control of risk, which I'm sure you know about from Network Rail. We get an attestation statement for the train, and we basically take that to the Great Western Safety Validation Panel, and we get an authority to proceed. And so this is the diagram that helped me stay sane and work out what was happening. It wasn't just me working on this, obviously there was others involved as well. I was mostly focusing on the train side of things, with others doing the Network Rail and the ASBO part of it. But it all had to come together. There's been several phases of this approval as well. There was the approval phase to get the train back on the main line, because previously it had been operated by Viva Rail, and the change of ownership and the modifications to it meant we had to get it reapproved for mainline use. And then there was so that got the train as far as West Ealing, down from Long Marston. And then there was the part of the approval to actually allow us to use the fast charge system, which was, I think we called that phase 2. And then there's another phase still to come to carry passengers. So it's all happening. Anyway, back to more interesting things. This is the obviously with the battery train, you're much more aware of the range limitation. Even with the charging system, you need to understand how far the train will go, what might affect the range. So if you get a fault, let's say 1 or 2 of the traction batteries no longer are available to you, then obviously you've got a third or 2/3 of the energy available. So you have to allow for that sort of thing happening, and also the fast charge system itself stops working for any reason. So we've got an undergraduate on our team called Jonathan Prince, who is doing a degree at Birmingham University. He joined Viva Rail 2 years ago as a 3 years placement, but then he carried on when Viva Rail went bust and joined Great Western. And he developed a mathematical model, which essentially models all the elements in the system, right from the traction batteries, motors, power electronics, charge rails, and all the inefficiencies that go with it. He put what do you call it? A modular model, which is what this is really. So you can sort of clip different elements together into this model. So you can have, if you wanted to, you can model a pantograph, different numbers of traction motors, different numbers of batteries, different ways of charging, different efficiencies in the system, and the output of all of this is these lovely graphs. So we modelled the energy consumption that we thought we'd get, and obviously we have to factor into it things like the mass of the train, the resistance coefficients, and all that stuff. And then that's just the train, but then you've got to look at the routes that the trains are running on. So you've got gradients to consider, number of stops, whether it's hot or cold outside makes a difference as well. So all of that is in the model, or is possible to be in the model. Passenger loading as well makes a bit of a difference. And did some wonderful simulations, got some wonderful results. But the key thing about any model is you need to validate it against real life experience. So there was a bit of that took place when the train was at COP26, but we only really had 2 weeks of data. One of the nice things about what we're doing now, and we will be doing for the rest of the trial, is getting huge amounts of data in different conditions, and we're actually setting up a very detailed test program for the entire year, which will essentially aim to validate the model. And that's important not just to prove that the system will work in all conditions, including failure scenarios, but also if we want to roll this out to other lines around the country, well, not just on Great Western, potentially elsewhere as well. And that's all very useful knowledge that's starting to build up now. But you can just from these graphs here, you can just see at the bottom right hand corner, this was, even the initial model was quite close to reality. I think the real energy use is the orange line, and the simulated energy use was the blue line. So it wasn't far off, but it could always be better, and it has got better since then. That was 2021. When we were doing runs on the Cotswold line in February, we were getting some very good correlation. So that was all good. So these are the simulated energy consumption results for the Greenford branch. It's a round trip of about 8 kilometres. Charging at West Ealing, as I say, so you've got to be able to get out and back as a minimum. But it only uses about 8.5 to 10% of the battery capacity in that round trip. So which equates to about 40 kilowatt hours, according to the simulations. So we've got to actually check this in real life, but simulations say actually that's not bad, which does point to the fact that you've got an awful lot of installed battery capacity on the train, probably more than you need. But what that does mean is that you can actually do probably 10 or 11 round trips with the fast charge not working before it becomes an issue for the train on that branch line. You've only got 3.5 minutes or so at West Ealing to charge, because we didn't want to require 8 to 10 minutes or anything excessive, because that would upset the timetable. So the fast charging time, you've only got that 3.5 to 4 minutes, and that is exactly the same length of time that the current diesel unit spends while the driver changes ends. That's the principle of the whole system. With this train, we've also got to get it back from West Ealing to Reading for maintenance. It doesn't go back every night. It only goes back every probably 18 weeks ultimately, because it's only got to go back every 18,000 miles. So that's obviously uses more energy. That's about a 50-kilometre single trip, and there are chargers at Reading depot, not fast chargers. They're just sort of plug-in chargers at Reading, so it can be plug-in charged before it comes back to West Ealing. Normally, the train is stabled at West Ealing carriage sidings, where again there are plug-in chargers for the train as well, for charging overnight. We've also looked at. I'll come on to that. We've also looked at the other branch lines: Henley, Marlow, Windsor and Eton, and yeah, just those ones. And potentially this system could be used down in Devon and Cornwall as well, or on other operators' branch lines. The question always arises: oh, how far will it go then? You know, if you didn't charge it, how far would it go? Well, you know, how long is a piece of string? It depends how you're using it. It's like an EV. Okay, so this graph will sort of tries to answer that question in a sort of logical way. I'm sorry. Well, let's say you were running it non-stop at 60 miles an hour on a flat route, no passengers, no heating or anything. Well, we reckon it would get about 140 kilometres doing that. Now, we sort of did that a bit when we brought the train down from Long Marston, this Chapel Avon, right down to Reading, and we did that in one go on one charge, and we reckon we could have gone further as well. So, but it was quite a favourable route because you go uphill to Morton in Marsh, and then you go pretty much down all the way to Reading. So, although we broke the UK world record, it was quite an easy time for the train, but we were very pleased it did it, obviously. Then, of course, if you put the heating on, that uses more energy, and it's actually quite significant. So if you take the same parameters there, look at the next blue line down, that's how much the range would reduce if you did the same thing but with the heating on. And then if you did the same thing but limited it to 40 miles an hour, so obviously not using so much energy to move, the range would go back up again, and so on and so forth. And you can see the effect of extra stops, gradients, and so on. So there's no right answer really. It depends how you use it. So you have to be very careful when answering the question. But you can just see there that the Greenford branch is where that green dotted line is. It's sort of in that area. But these are all the things we'll find out as we go along. So we had some fun testing the train out on the Cotswold line, up and down from Long Marston up to Evesham, down to Morton in Marsh. We did that for about 2 weeks to get confidence in the train again, having been stood down for over a year. Also to build up confidence in our range to ensure we could actually get to Reading without needing to be rescued, and that was largely very successful. One thing we did learn about the Cotswold line test runs was that driving style makes quite a difference, and obviously on the ground you can't really dictate to the driver how they should drive it. But what it did reveal was that the more the driver spends in sort of cruise control notches, as in power levels, the more energy is wasted. So normal driving style, if you like, is to accelerate up to line speed and then leave it in cruise control, which I think is sort of power notch 2 or 3, or 1 or 2. But if you tell the driver to accelerate and then coast, or do a sort of sawtooth profile, so up to speed, coast, a bit more power to keep the speed constant, you're doing a lot more coasting, and that actually uses far less energy. And the reason for that is because we've got AC traction motors, which are induction motors, and they have what's called energization losses. So as soon as you energize the magnets in them, they lose a lot of power, and that's quite inefficient. Which is why electric cars have permanent magnet motors. So another reason we were able to get it all the way to Reading and onwards to West Ealing was that we were able to sort of dictate the driving style, or advise which driving style to be using. The difference is illustrated here in these histograms. The top left one is just when the driver was doing normal driving, sort of no influence on that. A lot of use of power notch 1, 2, and 3, and then the second graph is when we said do more coasting, and it made a big difference to the range. So we brought it down to Reading initially, spent a couple of weeks in the depot just checking the train was compatible with the depot, making sure it could charge using the plug-in chargers. Then we brought it to West Ealing, did the same at West Ealing carriage sidings, and then eventually we took it up and down to Greenford. And it's just I like the picture on the left because it shows an underground train back in an underground station, but not an underground train anymore. It's sort of circularity of it's quite nice. And we had a media day, which was very successful. Lots of people attended that. We've since taken the train back to Reading because there was a bit more work left to do on the train. The heaters are actually too hot, so we had to sort that out. And we're also waiting to be allowed to use the fast charge system again because we had to get what's called a G99 agreement, which is, I think, Peter will correct me if I'm wrong here, but this is the agreement you need with the energy supplier to say you're allowed to connect a energy source to the grid. So there was a bit of delay in that for various reasons. So the train is currently hiding at Reading, waiting to come back at the start of June. But as I said earlier, the testing program from then onwards will be really up to and including a full day service. Now, the diesel train at the moment, the Class 165, does 31 round trips a day, and obviously our train needs to be able to do that day in, day out, 6 days a week, all year. The actual opportunity for doing that sort of running is limited because of the paths. And so I think we'll only be able to do it on Sundays when the normal passenger service doesn't run. But obviously the idea eventually is to hand over the service to the Class 230 and take the 165 elsewhere. And there's all kinds of other tests, as I mentioned before, that we need to do. We need to pounce on a really hot sunny day. We need to pounce and do various measurements. And equally on a very cold winter's day, we need to do certain measurements, make sure the charging system still performs as we expect it to. But fundamentally, it's about proving the system is reliable day in, day out, for a year. Oh yeah, these pictures just illustrate the kind of factors that we need to consider, from temperature to contamination of the rails. I mean, you do get quite a lot of litter building up around the charge rails. Now that could cause short circuits and all the rest of it. So that's something you need to consider. Passenger loading, we're probably going to get a load of volunteers to come and crush load the train from time to time. So if you want to be involved in that, let me know, etc. Yeah, not much to say really. Just a bit about the total cost of ownership, or the cost of doing this trial. One of the reasons for doing this, obviously, is that a battery train should be cheaper to run than a diesel train because there's fewer things to go wrong, fewer moving parts, and you're not burning diesel. So a while ago, we did a bit of sort of desktop analysis of what the actual cost of doing this would be. I took a study done by the European Union, or the EU Shift to Rail Joint Undertaking, I think one of their sort of research groups. That research was about hydrogen trains, and it's published in 2019, so I expect it's moved on a bit since then, but they produced some really useful figures in their report, which is all publicly available, about the comparative cost of maintaining a train. They looked at diesel versus fuel cell hydrogen versus normal electrified overhead pantograph train, if you like. They split it down into train maintenance, infrastructure cost, and fuel, and then you add those three things together to get the total cost of ownership. And what I did, I bolted on, while using the same methodology as best I could determine, I sort of bolted on the same analysis for a battery train. And what it shows is that, on the train maintenance side, a battery train should in theory be no more expensive to operate than a normal electric train. The first cost of building them is probably going to be more expensive because of the cost of the batteries. But after that, the actual running cost should be about the same. Infrastructure. Well, obviously, electrification is expensive, but has lots of benefits as well. So I'm not here to evangelise about battery trains being the complete saviour for when you can't afford electrify. But obviously, electrification is expensive. So you'd expect the cost of deploying this system to be a whole lot less. And it will be, because you've only really got the rails, trackside batteries, and the grid connection to think about. And in principle, you could install that system in one shift. You could put the rails down, connect them up in one shift. So that's, I think, quite an attractive feature of it. And then hydrogen trains sit somewhere in the middle. They do need some infrastructure, more than the average diesel train, for fueling purposes, because you've got to have very safe and high pressure fueling systems, which are not cheap. And the cost of hydrogen is also pretty expensive. And at the moment, I don't think it really compares with diesel. I don't think there's operators are now finding, particularly in Europe, that hydrogen trains are very actually quite costly to run. So there's a sort of, as a result of this, I think the cost of operation of a battery train is quite attractive, which is why you'll see others in the rail industry starting to really go down the route of battery trains or hybrid battery trains, which can use electrification to charge the batteries when available, but also run off the wire as well. We've done some work on embedded carbon as well, because that's something else people always say about battery trains and cars is, oh yes, well what about the carbon emissions in making it? We studied, or we broke down the carbon emissions of building or converting our Class 230. Now, the Class 230 is obviously an aluminium bodied train, 3-car train. It's had a life already of about 40 years, but there was energy involved in actually converting the train. So we broke it down into the cost of the materials, and we also considered the cost of the factory, the old Beaver Rail factory in Southern. For example, that was heated by gas. So as you can see, gas was quite a large part of the embedded cost of building that train. And then we took the materials part of it and split that down further into the battery itself, aluminium, steel, plastics, etc. And worked out that it probably cost about 255 tons of carbon to convert that train. Now it would be probably more for a brand new train, but that's the sort of order of magnitude that we're talking about. And then we looked at the actual emissions from running the train, which is what this graph is. So obviously, depending on the mixture of your grid, we're charging the train from the grid, and the grid at the moment is not fully decarbonised. So there's a carbon cost of using the national grid. But you can see here that the emissions from diesel soon racks up. That's the dark green bar. That soon racks up over the years. Whereas the emissions, if you like, from the battery train, although there's no local emissions at West Ealing, it's all zero emission at the point of use. Obviously, the emissions are there in the background. So but even with that, it's a much more environmentally friendly thing to do. And I think when you look back at the embedded carbon of building the train, I think we worked out that you sort of get a payback within about 11 months compared to running a diesel train. So you soon get the payback. And I think finally, this is just to illustrate that we could do this on other branch lines. We've looked at them. We've made a proposal for DFT. Whether it will get to light today, I don't know. But in principle, you could put fast charge battery banks at Slough and Bourne End and Henley on Thames, and you could run Class 230 or whatever on those branch lines as well. It's all eminently feasible. Each location's got its own challenges, whether it's finding the space to put the battery banks or whether it's a constrained grid connection. There's actually a tool you can use. But there's a tool you can use to determine how constrained your grid is in various locations. And I think somewhere like Slough is pretty easy because they've had lots of industry in the past using electricity. But somewhere like Henley, I think, is less easy to get a grid connection. And we are talking probably 3 to 4 years to get a grid connection. So we're told the DFT that if you want to do this, you need to decide soon because of the lead time for that. So, and that's it really. So over to you for questions. Hope you enjoyed that.
Thanks very much, David. Have we got any questions in the room? Wow, this is good. Let's start at the front. Yeah, go.
Sam Jones, Amy. Thanks, David. Just a question about, obviously, the Great Western Main Line is electrified.
Yes.
Has there been any thought about how the 25 kV system could be used rather than some of the fast charging?
Well, it could be. I mean, if you buy a fleet of battery trains that charges from the overhead line, they could run on the branch lines as well, and probably have enough. Yeah, they certainly on Thames Valley, you have enough installed capacity on those sort of trains to charge them on the electrification and then run them off the electrification for those branches. So that's possible. And I suppose in hindsight, this system is probably better suited for areas of the country where there isn't electrification anywhere nearby, like in Devon and Cornwall. It just happens to end up on the Greenford line as a good place to try it. So I think I should also say we've worked with the RSSB, and they've got a project T1272 looking at different ways of charging battery trains. And obviously we fed into that and said, well, our system does this, and then other manufacturers have got different systems. And I think they've concluded that I think by and large most battery trains in the future will be charge from the overhead, but there will be some locations where this sort of thing would be useful and probably more beneficial. So by no means is this going to be, you know, the system for charging battery trains, but I think the one thing it has got going for it is it's here now. It's you know, it's working, and particularly for the Thames Valley branch lines, we could do this in the next few years if the DfT gave us permission to do it, and we put our minds to it. So as a sort of interim step in the right direction. And I say it's got other benefits as well. With the trackside battery banks could be used to stabilise the grid, and there's a monetary value to that as well. So if Network Rail or GWR want to sort of take advantage of that in future, then that could be another income stream as well. So, yeah.
And the other thing is with the containers, the battery containers, of course, that they can take cheap electricity off the grid at night.
That's it, yes.
Rather than during the day. Going back to your question, then the overhead's a single phase. This is a three-phase system. Charging system three-phase, so there'll have to be extra work done on that. Not sure whether there'll be much advantage taking 25,000 watt system as opposed to taking from the 11 kV system. Three-phase.
Okay. Next,
I think it's almost similar question. The only thing is, did you check the possibility of having these shoes going upwards? So having just like catenary type. So it's
Oh, right. Yes, I mean that would be possible. It obviously isn't designed like that, and it would come with its own challenges. But I mean, there's potential advantages to doing that in that it suffer less from contamination.
yeah, fixed rates.
Yes, yeah. We'd have to put a lot of equipment on the roof of the train, which would be challenge on these trains. But yeah, in principle, you could do that. We probably won't, but not now.
okay, there was another hand up, I think. No, imagine
Yes, I got one. Just sorry, in terms of the different battery types have different sort of preferences on how much they should charge or how much they should lose, sort of if they should be degraded a lot and then charged up, or if they should be kept at a high level.
Yes, they do. And we try and keep ours between 20 and 80%. The 80% so that you can use, so you've got enough headroom to use regen braking to put energy back into the batteries. 20% just to, well, it's very hard to work out, but the manufacturers have their own margin, and then we have our margin, and it's hard to tell. And there's no such thing as state of charge. There's no actual, you can't really measure state of charge. You have to measure volts and amps, and then derive it from that. So, but essentially, we try and keep it between 20 and 80% as a nominal figure, and it does depend on the chemistry because we've got this onboard thermal management. It's always permanently, monitoring cell temperature, cell voltage, cell balance as well. So, yeah, I mean, different types of electric vehicle are different, again, but that's the sort of range we're working to.
How long does that give you in terms of, because batteries don't last forever, do they?
No, well, we don't really know is the honest answer until we've done this trial and had it running for many years. It's the manufacturer always said, oh, they'll last for 8 to 10 years or something like that, which is great. And even then, after 10 years, it doesn't mean they're completely kaput. They'll still have a usable capacity. Whether you could in theory take them off the train, remanufacture them, put them on the trackside battery banks as a sort of second life, and after that you could take them out of there and put them in for home storage, and then after that you might end up recycling them. So batteries may actually have 2 or 3 lives before you actually end up having to rip them apart and recycle them. And that's something we want to, if we were to roll out another, a fleet of these trains, I think the spec might say, make sure you can use the batteries from from train onto trackside battery and all the rest of it. At the moment, they're 2 different manufacturers, so it's only a theory. But I think battery recycling is getting better and better, driven by cars and trucks and all the rest of it. They'll always have to lead over rail, but I wouldn't be surprised if the batteries will last 10 years or more. And okay, we won't know until we've actually run the train for many, many years.
I've got a few online.
Yeah, I've got one actually. So I'm going to take you to track components because that's the thing I know and love. So the base plates and the charging rails, are they all based on standard components,
Yes.
standard rail sections?
That's right, yeah, it's all,
So it's all off the
so like
shelf.
with companies called Fuse Rail, and it's, I think it's off the shelf. Third rail, isn't it, BT?
Yeah, well, the stainless steel covered rails, I'm not sure about, but the rest of the road definitely.
Okay.
Yeah, including the method of how they secure them to the sleepers and such.
Yeah. Okay, we've got some online.
Yeah, we've got quite a few online. So if I'll ask people to come off mute and ask a question themselves. So Stephen Bickler, could you come off mute and would you like you to ask David your question?
Yeah, thank you. I was just interested in that mention of RSSB because I did a comment at one time under Nick on energy and decarbonisation, and they were interested in all of these options. So how's the RSSB interface looking at? What are they going to be publishing on this, if anything?
Well, they published just recently, I think just this month or possibly last month. If you look for T1272, they just published that study in full, which is, I can't remember the title of it, but it's to do with it's to do with charging systems really, and sort of assessing what's out there at the moment, and sort of recommending what I think they've gone for 2 or 3 different types to be the sort of, they're not standards yet, but I think the next stage is that RSSB will start working on standards for this. And we'll be involved with that as well. The Railway Industry Association has also just published a really good report about a net zero railway by 2050, and that basically recommends that another third of the network is electrified, but the remaining third of the network would be operated by battery trains. So that's worth a read as well.
Thank you.
Is the TM55, the other one?
Not heard that one, no.
No, that's about embedded carbon and running carbon.
Okay.
A lot of manufacturers are now happy to go for it.
Yes.
What it is.
Yeah, there's a certificate I think you can apply for, and we're going to try and do that so that everyone says when we've got the same certification as other manufacturers. Not that Great Western's a manufacturer, but to essentially go after this train.
Pernell has got a question. If you'd like to come off mute and ask a question. Okay.
Hi there. Good afternoon. Yeah, my question is just basically about the regenerative braking also being a source contributing to charging. But I just wanted to know, would that be an added benefit to this rapid charging trains, or something along those lines?
It's not as much of a benefit as you might think. I think we've calculated it'll be 5 to 10% of the energy, or it's not a huge benefit, but we will be doing regenerative braking. At the moment, it's isolated for various reasons, but it will be able to regenerate back into the batteries. And obviously, the hillier your route and the more stops you've got, the more of a benefit it is. I think Greenford's a fairly flat route, so you only really get it back when you're stopping for the stations, and you don't get a huge amount back. So you won't want to rely on it, but it is a benefit, yes.
Thank you.
Great, thanks. Simon Bjork has got a couple of questions. If you'd like to come off mute and answer.
Hi, good afternoon. My question is, how do the comparative costs between fuel sources compare, factoring the periodic capital cost of replacing the batteries, maybe over the typical lifespan of a passenger train, 30 or 40 years? And then second to that was, with ultra fast charging, would that adversely affect the lifespan of the batteries?
On the first question, I don't know, I'm afraid. I haven't done that calculation. But obviously, you do need to factor in on the overall life cost, you need to factor in the possible replacement of the batteries. But because we don't really know how much that was actually going to cost, I didn't actually factor it into my total cost of operation calculations. The second question about how much does fast charging affect the battery life? Well, again, because the batteries are designed to a certain charge rate, it shouldn't adversely affect them, and that's because of the thermal management on them. If you were if you were aggressively charging and discharging a battery that's not designed for it, then yes, it could have quite a significant impact. And again, it's something we don't really know until we've run the trial and measured the relevant parameters. So, and this is because we're kind of at the start of the technology journey as far as rail is concerned. The automotive will have a lot more data on this, but in terms of duty cycle for battery trains, then we're at the start of that learning curve, so we don't know.
Thank you.
Saran, you've got your next up. I think you've got a couple of questions and there as well as a couple of comments.
Yeah. Hi all. I've got a few points, but I mean, I'm really impressed with the 4-minute full charge. That's a great seller if you're going to move forward with this in a big way. But I think part of this may have been already answered. Is this where OLE isn't available, or is it going to be used like a backup, or would this solution be better used in remote areas?
Yeah, at the moment it's going to be used where OLE is not available. So, well, at West Ealing obviously it is, but it's Bay Platform 5 is not electrified. So, although it's adjacent to electrification, it's not actually available to the Greenford service. But I think yes, this technology will have more of a application in rural areas where you're a long way from electrification. And of course, the emerging concept now for sort of longer distance trains where a lot of the journey is not on electrification is to have islands of electrification, which is also a good idea. But also that comes with a cost and requires a high voltage connection, etc. So maybe there's somewhere between this fast charge system and electrification where you could have electrification with trackside storage as well. I don't know.
Okay. I mean, working on CVL, as you know, parts of the the routes or the system is going to be OLE driven. Others going to be pairs and battery power. Combination, which is a great way of moving forward. I think in that sort of area, if you like. So yeah, I think there's a case for it, definitely. The other point I made was that has this system been fully tested in flood related areas, particularly I think it's being forecasted, at least in South Wales, that over the next 50 years or so, water levels are going to rise. So I know stations are designed such that we don't suffer from that, but there could be situations where, you get flooding, and in those cases, would it be safe to use that system?
Yeah, we haven't actually tested it underwater, but obviously there is allowance for flooding. There's this thing called a bender relay, I think it is, which basically looks for current leakage. Is that right, Peter?
Yeah, that's right. It's no different than any other train. Once the water gets to the rail level, then that's it. Drivers don't tend to want to run. If you're worried about the charging rails, yes, it will measure and measuring nearly every time it said as the pickup comes down onto the rail. If there's a leakage anywhere, it will just retract and won't charge. The red light won't come on.
The fail system in place.
So, but no train will be running if water's above the rail level.
I mean, the charge rails themselves sit, the top of the charge rails sit above normal rail level anyway, just like the third rail. So there's a bit more, but obviously the bottom of the charge rail does sit in the forefoot in the area which might get flooded. So, but as we said, there's a relay that looks for earth leakage and would switch the whole system off straight away in that eventuality.
That's good. My final point. A battery use is big for the future, as you've seen plenty of publications on this, particularly in the auto car industry. So, I mean, it's something we're not going to get away from. But I was just thinking that, is there another organization developing something similar, perhaps elsewhere in the world? As you know, funding is always key in these things to take things, make them commercially viable. Perhaps if there is elsewhere in the world, we could team up with them and, improve our chances of sort of a worldwide use if possible, in some areas.
Yeah, I think there's several answers to this question. One is rail tends to buy equipment as a kind of black box, I suppose, and that's what we've done with the batteries. We've ended up with a battery raft from a supplier that was already validated to, have already supplied to rail companies in Europe and all that. So it was quite easy in that respect. Right, buy that rail approved battery raft, if you like, and it is what it is. If I had complete freedom and I could go back in time, I would design a battery for the Class 230 that was much more gauge friendly and much more distributed in terms of the weight. And you could make much better use of the space if you actually had a battery that was designed for the underframe. Now, if you look at other trains in this country that have got lithium-ion batteries on them, so the Hydroflex, which I mentioned earlier, has actually got a big lithium-ion battery on it as well, which is has been designed much more for that application. We ended up with battery rafts the size they are because we were trying to replicate the old diesel gensets that we had underneath. So we've kind of ended up at that solution, but it wouldn't, it wouldn't start from here. You sort of what I mean. And if you're designing brand new trains, you've got much more freedom. What I would probably do is do it like EVs and build the batteries into the floor, or have them actually just so you can distribute the weight, distribute the power, and then have much more energy dense as well. Much more gauge friendly, much more mass friendly. You could do a lot with it with a new train. Less so with a retrofit like what we've got. And in terms of different battery chemistries, we should definitely keep a close eye on what others are doing. I mean, sodium batteries are very interesting because that potentially has the opportunity not to use the precious metals. I think there's a company in Cornwall, I think it is, harvesting lithium from seawater as well. Sorry, not so much for sodium batteries, but for lithium batteries, there's a company doing lithium harvesting or looking to do that. So there's all kinds of interesting things, and we just have to keep an eye on the automotive sector, really, and the universities and everyone else working on it, because there might be something out there in 10 years' time that will be applicable to rail. In fact, I've no doubt there will be.
Yeah.
Siemens have just launched, just into service, a battery, 3-car battery train for internal to Germany. They're doing the testing the same as we are. They've had a blank sheet of paper.
Yeah.
So there are companies there, and I know China's got one, and now China's got a bus, a spendy bus with battery, and they put their shoes, they come down on top of the bus.
Yes.
So the bus, instead of running over a collector thing, as it hits a bus stop, the shoes come down on top.
Yes, just like this gentleman said. Yeah, that's it.
Yeah.
Okay, we are at 5 to 2. I think there's 2 more people online, and then I think we'll have to
Thank
call
you.
it quits. Thank you.
Thank you.
Leo Lai, you've got a quick question, I think.
Yeah, sorry, I've got a quick question about the entire fast charging mechanism. So can I know, will it intend to become a national standard in the foreseeable future? Or is this method under some negotiation with DFT and other potential manufacturer?
Well, DFT don't really know what to do with it because they wanted the trial to continue. So they made the arrangements to pick up the pieces of VivaRail and re-employ us and get things moving again, which is great. But obviously DFT and or Great Western are not equipment manufacturers. So as to whether this becomes something that other train manufacturers pick up on, I don't really know. I'd love to think that will happen. In terms of becoming a standard, that is probably a bit more advanced because the T1272 RSSB study I mentioned earlier advocates for what they're calling a buffered ground-based charging system, which is basically our system, buffered being the energy buffer and ground-based being what you see. I think that will gradually progress towards becoming a standard for UK anyway. And if manufacturers want to use that system, they can. There'll be nothing stopping them. It just requires the DFT own the intellectual property at the moment. So that's interesting. Can you imagine? And decisions will have to be made and thoughts will have to be, had about what happens to the intellectual property and this system, because currently we're living in the sort of, well, get this done, and then what happens next? It would have been different under VivaRail because for VivaRail it was a product and they would have been looking to sell that to manufacturers and all the rest of it. But at the moment it's just get this to work and prove that it's reliable. So.
Okay, thanks, Leo. Thanks.
Nice to hear. Thank you.
And the lucky last question goes to K.A. Aney.
Hi there, Kay, Amy. Thanks for the great presentation. My question was, I just wondered whether the current FCCB locations proposal aligns with existing sidings and depot locations at all, in the interest of cost.
Oh, you mean on the potential future rollout?
Future, yes.
Yeah.
Yes.
Obviously, the preference would be to keep them on Network Rail land. But I think for permitted development, that would be easier.
Yeah.
In those locations, there are no sidings, as far as I remember. They're all just single track branch lines with no other facilities around them. They're all passenger branch lines. I think there's no freight. So, but yeah, the preference would be to site fast charge battery banks on Network Rail land wherever possible. Although you could see a scenario where you might put them in a car park, which may belong to a local authority, and with a slightly bigger battery bank, you could charge other modes as well. You could charge cars and bikes and whatever and that could be a source of income for the railway.
Like it. Yeah. Okay. Thanks everyone online for the questions, everybody in the room. Quick round of applause for those that are left. And thank you, David, that was superb. Loads of interest, and the numbers online kind of back that up. There's obviously a lot of people keen to understand what you're doing. So thank you very much. Let everybody get back to work now. We've run on long enough, but see you next one.
Thank you.